Ladies and gentlemen, I would like to welcome you to chapter 16 of Chem 2B. There is something about aldehyde and ketones which makes them very important to us. So what are the factors which makes these very popular? One reason is presence of this group. If you look at this structure, the black atom is carbon, oxygen is a red atom, and there is a double bond here. This group in aldehyde and ketones is called carbonyl group. It's the chemistry of carbonyl group which makes them important. I'm going to look at the structure of carbonyl group. So let's look at some of the examples of aldehyde. This is ketone. This particular ketone is called acetone. So it has got a carbonyl group which is connected to two carbons. And this is called an aldehyde because the carbonyl group is connected to one hydrogen. And this is also an aldehyde again because the carbonyl group is connected to one hydrogen. So the difference between ketones and aldehyde is the fact that in ketones, you have got two carbons connected to carbonyl group. In aldehydes, one of the carbons are replaced with hydrogen. So this is carbonyl group that we were talking about. A carbonyl group, it's simply a carbon-oxygen double bond. So you have a carbon here, which has got one orbital, another, and we said these orbitals are called sp2 orbitals. And then there is a p orbital, which is not hybrids and sitting on carbon. And then we have got oxygen, which also has got an orbital here, and it has got two lone pairs, and there is also a p orbital on oxygen as well. So what is happening is these two orbitals can have head-on overlap. The result of this head-on overlap is a very stable bonding, which we call it sigma bond. And then the two p orbitals, let me show you a little bit higher here so you can see better. The two p orbital, they have half lobe on the top of the plane of the molecule, and they have two half lobes on the bottom of the plane of molecule. These are the two p orbitals. They don't have a choice, but they can do side-by-side overlap. The side-by-side overlap is not very efficient, is not very effective. So these side-by-side overlaps are called pi bond. This is half of the pi bond on the top, and the half of the pi bond is below the ring of the molecule. Because pi bonds are not overlapped very well, they're very reactive, they easily open up. So this is another way of showing overlap between side-by-side overlap between p orbitals making a pi bond. Also, another important factor which is responsible for reactivity of carbonyl group is the fact that the bond between carbon and oxygen, carbon has electronegativity of 2.5, oxygen has electronegativity of 3.5. So you see the difference between these two is about 1.0, and that's large enough to make this bond polar. The more electronegative carbon is going to pull electrons from the double bond. So there is more electron cloud on oxygen end of carbonyl group, and the carbon part, which has lower electronegativity, has shortage of electron cloud. As a result, it has got positive charge. So can I say that carbonyl bond is polar? As a result of this polarity, carbon is carrying a positive charge. Oxygen is carrying negative charge. So that makes the carbon of carbonyl group very sensitive to electron attacks, so electron source. Electron sources would love to attack this positively charged carbon, and that makes the chemistry of aldehyde and ketones that explains a lot of reactions of aldehyde and ketones. So I have some aldehyde ketones here. This is called formaldehyde. That's the common name. But the IUPAC name is methanol. So where is the name of formaldehyde, the common name is coming from? It's coming from the fact that this is a structure of formic acid. And therefore, the aldehyde is called formaldehyde. That is the common name. But IUPAC name, international nomenclature, is much easier. What would you have called this hydrocarbon with one carbon? Would you have called it methane? So take the hydrocarbon and then remove the ending, remove the E at the end of methane, and replace it with all, which shows aldehyde. So the name of this is going to be methanol. So this is the name, methanol. That's the name of this aldehyde. But if I look at hydrocarbon, if I had a hydrocarbon with two carbons, what would you have called that? Would you have called that ethane? Remove E and add all. Would you call it ethanol? That's IUPAC name. What if I had a hydrocarbon, if I had an alkane with three carbons, what would you call it? Propane? No, this is an aldehyde. All I have to do, remove E and add Al, all. So propanol, that is the name, or IUPAC name of this aldehyde. Now, what is the common name? Propion aldehyde. In this case, ethanol has a common name as well. The common name for ethanol is acetaldehyde. Where is acetaldehyde coming? Acetaldehyde is named after acetic acid. Acetic acid has got two carbons. That's the acid in vinegar. And what would be the IUPAC name of this aldehyde with four carbon? Now, four carbon would have been butane, right? Butane. I'm going to remove E and add all. Can I say the IUPAC name is butanol? Butanol, and common name butyraldehyde, coming from butyric acid. Butyric acid has got four carbons. So common names shows relationship between aldehyde and their acid, mostly, and international name, take the name of the alkane, remove E and add Al. I hope this makes sense to you. So this is a good point to stop, and we will come back in the next video. Thank you, guys.